A support message lands while you are eating lunch. It says they closed their account 3 weeks ago, and they have just signed in again, and they can still see everything they used to see. You open your own database and the account really is closed. You open your own logs and the request really was allowed. Nothing was hacked and nothing was forged. So how does a closed account keep walking through your own front door? Hold that question. We will come back to it at the very end, because the answer is the whole difference between a badge that gets checked and a badge that merely gets read. Here is the sentence you have written in a design document, or heard in a conference talk, or nodded along to without turning it over. We use signed tokens so the server never has to remember anybody. Simple. And it sounds like a complete account of what you built. But that is not a mechanism, it is a slogan. It tells you what you stopped doing. Does it tell you what you started promising? It does not, and the promise is where your incident lives. Every stateless design moves work somewhere, and if you never say out loud where the work went, the work is not gone. It is just unowned. Let us try again. Maybe the difference is that a session lives on the server and a token lives on the client. That is closer, and it is still furniture rather than physics. It tells you which library to install. Does it tell you which check you skipped? It does not. Let us try this one more time, and this time build the thing instead of naming it. Where does the work go when you stop remembering anything? Watch what happens as the system grows, because the answer arrives on its own. Say your team ships a shared reading list called Waypost. Version 1 keeps a table of sessions. When somebody signs in, you write a random identifier into that table, hand it back as a cookie, and on every later request you look the identifier up. Where does the truth about who is signed in actually live? It lives in your database, which means you can change it whenever you like. Remember that sentence, because it is the property you are about to sell. Then Waypost gets popular and you split it into several services. A list service, a comment service, a search service. Now every one of them needs to ask your session table who the caller is, and that table becomes the busiest thing you own. You want each Waypost service to answer for itself. So you stop storing sessions and start signing statements instead. That signed statement is what people mean when they say JWT, the JSON Web Token, standardized by the IETF as Request for Comments 7519. It has 3 parts, joined by dots. The first part is a header naming the signing algorithm. The second is the payload, a small set of assertions about the bearer. The third is the signature over the first 2. Which of those 3 parts do you think a stranger is able to rewrite? Hold your answer, because it is not the one most teams guess. The signature is the entire trick, and it is worth saying slowly. The Waypost issuer takes the header and the payload, runs them through a signing algorithm together with a secret or a private key, and appends the result. Any service holding the matching key can recompute that signature and see whether the token was altered. So the truth is no longer in a table you own. It is in mathematics that every Waypost service can check on its own. Notice what that buys and what it costs at the same time, because a fact you can no longer edit is exactly what it sounds like. Note, the first 2 parts are not encrypted, only encoded. Base 64 is a transport convenience, not a lock. Paste any token you own into a decoder and you will read every claim inside it. So a token is a postcard with a wax seal, and the seal proves nobody rewrote the postcard. It does not stop anybody reading it, which means anything private has no business being in there. Are there internal identifiers, role names, or email addresses in yours right now? Whatever is in there, treat it as published. The claims themselves are where security actually happens, and each one exists because a team somewhere was burned without it. The issuer says who made the statement. The subject is the stable identifier for the person. The audience says which application the statement was made for. The expiry says when it stops being true. There is also the issued at time, the not before time, and a token identifier for when you need to name one specific token later. Which of those does your own code actually read? That is not a rhetorical question, and the honest answer is usually 2 of them. Analogy, think of a wristband at a festival. The seal on it proves the gate fitted it rather than somebody at home with scissors. The printed date proves which day it is good for. The name of the stage printed on the inside proves which entrance it was cut for. Every claim is one of those printed lines, and a check you skip is a line you never looked at. Now hold on to that image, because every failure in the next few minutes is a line somebody printed and nobody read. Now watch how this goes wrong, because the interesting part is that almost none of the well-known failures involve breaking any cryptography. The first one is the algorithm named none. The original specification really did allow a header that says this token is unsigned, and several early libraries really did honor it. A stranger hands Waypost a token, edits the payload so the subject is your own administrator account, sets the algorithm to none, deletes the signature, and your library reports a valid token because it did exactly what the header asked. Who chose the algorithm in that story? The attacker did, from inside the message being checked. The second one is subtler and it still ships today. Suppose Waypost signs with the asymmetric algorithm RS256. Your private key signs, your public key verifies, and you publish that public key so every service can check tokens without holding anything secret. Now the attacker takes your published public key, treats those bytes as a shared secret, signs a token of their own choosing with the symmetric algorithm, HS256, and sets the header to match. A library that reads the header to decide what to do will verify happily, using a key you handed out on purpose. That family of bug is called algorithm confusion. Both of those have the same shape, and the shape is what you should carry away. You let the message tell you how to judge the message. So the rule is not a longer key or a newer library. The rule is that your verifying code names the one algorithm it accepts, before it looks at anything the caller sent. The third failure needs no attacker cleverness at all. Every library ships a function that decodes a token without checking the signature, because there are honest reasons to want one, such as reading the expiry for a log entry. That function sits one letter away from the one you meant, its name is inviting, and it returns exactly the object you expected. Search your own codebase for it right now. Is every hit somewhere a lie would be harmless? That is the question, and in most reviews the answer is no. The fourth one is the audience claim, and it is the same defect that has closed more security tickets than any exotic attack. The Waypost search service checks that a token is signed by the right issuer and has not expired, and then trusts it. Somewhere else in your company, or in a partner integration, the same issuer mints tokens for a different application. Those tokens are genuine. They are signed by the key you trust. They were never meant for Waypost. Unless you compare the audience against your own identifier, you accept them, and nothing in your logs will look unusual. The fifth one is time, and it is where your lunchtime incident starts to come into focus. The expiry claim is only as good as the clock reading it. If one Waypost service runs a few seconds fast, freshly issued tokens look invalid, so somebody adds tolerance, and tolerance quietly becomes generous. Allow about 60 seconds of clock skew and refuse to go further, because every second you add is a second a dead token keeps working. Which brings us to the thing tokens genuinely cannot do, and the reason your closed account walked back in. A signed statement is true because of when it was made, not because of what is true now. The first Waypost could revoke somebody by deleting a table row. The Waypost you have now cannot, because there is no row. You did not remove revocation when you went stateless. You moved it, and nobody caught it. So what do serious systems do about it? They make the window small and pay for it somewhere else. The access token lives for something like 15 minutes and carries the claims a Waypost service needs. Beside it sits a refresh token that lives for days or weeks, is stored where only your issuer sees it, and is checked against real estate every time it is used. Now the worst case is a stale answer that lasts a quarter of an hour rather than forever, and you get your revocation back at the refresh step. If a quarter of an hour is still too long for you, and for some actions it should be, then you keep a small list of tokens you have cancelled and check it on the operations that matter. Notice what you just rebuilt. You are looking things up in shared state again, on purpose, in the places where being right beats being fast. Stateless was never a property of your system. It was a property of one code path. There is a cheaper form of the same idea that costs you no list at all. Keep one counter per Waypost account and copy its value into every token you issue. Bump the counter when somebody signs out everywhere, changes a password, or closes the account, and compare it on verification. You are back to one small read, but it is a read you already do. Where the token lives on the client is its own argument, and it is worth being precise instead of dogmatic. Put it in browser storage and any script running on your page can read it, so one bad dependency is one stolen credential. Put it in a cookie-marked HTTP only, secure, and same site, and script cannot read it, but the browser now attaches it to requests you did not write, which is what cross-site request forgery protection exists to handle. There is no option here that removes work. There is only a choice about which work you would rather do carefully. Case in point, Auth0, Okta, and Keycloak all issue and verify these tokens for a living, and all three publish their signing keys at a well-known keyset endpoint so your service can fetch and cache them by key identifier rather than pinning one forever. Kubernetes uses signed service account tokens for workload identity, with audiences bound to specific services precisely because of the fourth failure above. Firebase issues them for client sessions. The Python library PyJWT and the Node library called JSON Web Token both now default to requiring that the algorithm be named, which they did not always do, and both still let you switch every checkoff with one keyword. That last detail is the honest shape of this whole subject. The dangerous settings are not hidden. They are documented, sensible sounding, and one argument away, and they get switched on by somebody in a hurry who needed the failing test to pass before stand-up. Quick win: open the file where your service verifies a token. Read the call and answer three things without scrolling. Does it name the exact algorithm it accepts? Does it compare the audience with your own identifier? Does it use the verifying function rather than the decoding one? Those 3 lines are the distance between the incident you opened this episode with and a quiet afternoon. Note, if you sign with HS256, the shared secret is a cryptographic key and not a configuration string. A dictionary word can be recovered offline from a single token, at which point anybody mints your tokens forever. Use at least 256 bits from a random source, keep it out of your repository, and give each environment its own, so a leak staging secret cannot sign production. Caveat: none of this protects you from your own claim design. A token that says the caller is a site administrator is only as trustworthy as the code that decided to put that in there, and every service downstream will now believe it without asking. Signature verification tells you the statement was not altered. It says nothing about whether the statement should ever have been made, and teams consistently underestimate how much authority leaks into a payload once it is easy to add a field. 2 opinions will now form on your team, and each of them is holding something real. One says tokens made your services independent and you should never go back. The other says you traded a problem you could see for a problem you cannot, and sessions in a fast shared store were never the bottleneck anybody claimed. Both are right about what they are looking at, and the reason they disagree is that they are not talking about the same requests. So sort your requests instead of your opinions. Reading a public list can be answered from a token alone and nobody is harmed by a stale answer. Changing a password, moving money, or removing a person from the account may still require a fresh look at real estate, and those endpoints are a small fraction of your surface. The design question is never tokens or sessions. It is which of your operations may act on a statement made 15 minutes ago. So back to the question we opened with. The answer is that nothing about that request was wrong. A closed account signed in again because Waypost was reading a statement that had been true when it was issued and had no way to learn otherwise, and because the window you left open was measured in hours instead of a quarter of an hour. Your logs recorded a success because a success is what happened. The defect was never in the request. It was in the promise nobody wrote down. Before you touch any of this, ask yourself these 5 questions, in this order, and answer them out loud. Which of my endpoints may act on a statement made minutes ago, and which must not? Does my verifying code name its algorithm and compare its audience? How long is my window, and who decided that number? What happens the moment somebody closes their account or changes their password? And what would I have to look up to notice if any of those answers were already wrong today? If some of those answers are uncomfortable, that is the useful outcome. Signed tokens are not a safer kind of session. They are a different bargain, and every clause in it is your call to make. Decide for yourself how stale each answer may be on the endpoints you own, write that number down where the next person will find it, and set the terms before somebody else sets them for you at lunchtime.